let me record then. And let me share the screen. Yeah, so we were discussing the high dimensional integration, and the discussion last time I noticed was not very easy to understand, was not very methodological. So today I wanted to explain the same thing in a different way, and I hope that this one is going to be more clear. So the Markov chain is used for many things. We used it to simulate Ising model because that's one of the simplest applications of it, but it's very, very useful in several other applications. One is high dimensional integration. The other one is minimization of a function. Now, first I'm going to discuss high dimensional integration. So what do we do? Well, the goal, of course, is to integrate a function which is a function f of x. X, it has many, many components, and this n is very large. It can be high, it can be 100 dimensions, can be maybe 500,000 dimensions. Of course, when n is extremely large, or when n is millions, then that problem becomes extremely hard. But at least a few hundred dimension is completely doable. So what do we do? Well, we construct a Markov chain in this case, but the question is, what do we take for probability, or basically this density, probability density, isn't that rho of x? So recall that in the Ising model, we took rho of x to be this e to the minus e of x divided by z. Remember Boltzmann. So the idea in Markov chain was, let's take the Boltzmann distribution because that's how states are distributed. Actually, there's divided by t, it's Boltzmann, so it's a mistake. Divided by t, so this is Boltzmann. So why? Because, well, in physical systems, that's how the energies are distributed according to Boltzmann. Now, in Ising model, I didn't emphasize that, but the point is that in Ising model, we don't know z, okay? We don't know z. We never computed z. Partition function, so, or equivalently free energy. So we computed free energy with one Landau algorithm recently, okay, and but not with directly in simulation of the Ising model. We could compute specific heat, that's fine, and we could compute the total energy, but we never computed entropy. So in entropy can be computed only with one Landau algorithm. Okay, one Landau algorithm is unique in the sense that it can give you entropy. If you just simulate Ising model the way we did it first, there is no way to calculate entropy. It's a well-known problem that entropy cannot be obtained by direct simulation. Now, but the fact that you cannot calculate entropy is equivalent to say that you cannot calculate z, because if you know z, partition function, then you know that the free energy is minus T log Z, and if you know free energy, then of course you know the entropy, because we know that free energy F is E minus Ts. Of course, energy is easy to compute, but the temperature entropy is the harder part. So the point is that if you know Z, you definitely know entropy. But you don't. If you do direct simulation, you cannot calculate z. Now, why do I emphasize this so much? Because if you do the direct simulation, we say that probability is this e to the minus e of x divided by t divided by z, but we don't know the z, which means that probability is only proportional to this e to the e of x divided by t, but we don't know the proportionality constant. Okay, z is like proportionality constant. Now, the point is that this, in Markov chain, this proportionality constant is always kind of hidden. It always cancels out, and we don't know it. Okay, so why? Well, in this particular example of integrating the function f of x, I told you that we're going to take the probability to be proportional to the absolute value of the function, and then we will add to it some some other function for which we know the integral. Okay, and this alpha is some constant, doesn't matter so much. We're going to discuss what's the best alpha, but for now alpha is completely arbitrary. Now the point is that the real probability density is going to be constant times this thing, and we don't know the constant. Okay, that's the issue. That's the issue. That's the issue why we need to add this extra function, because if we knew the constant, we wouldn't need to add this extra function in order to know the integral. Now, let me explain why this constant is not known. Because let's say that our trial steps are symmetric, because that's the easiest. Let's say that we do simple trial steps such that we just we just change, let's say, one of the x's, one of the x points, okay, in one dimension. So this is symmetric, so we can remove, we can forget about trial step probability. Then the transition probability is just this simple thing. It's either 1 if this ratio is bigger than 1, or it's this ratio between the old configuration and the new configuration, as that. So we discussed this before, how the transition probability is the ratio between the two rows, isn't that? The row of the new configuration, well, you have to divide by the, so how do you have to take the new configuration divided by the old configuration, yeah. Okay, so now the point is that you see, when you calculate actual transition probability, you see this constant C is cancelled, okay? And so basically we don't know this constant. It's in our entire procedure, when we visit things, this C is irrelevant, can be anything, and we don't know it. So therefore we can always determine things up to this constant C. And this has a consequence that if you take the rho of x to be just absolute value of function of x, you will not be able to determine the integral. Okay, let me show you why. So up to now, I'm just telling you the recipe, and I'm not proving anything. I'm going to prove in a second. So right now, the recipe is the following. We take the probability to be proportional, to be this constant, some unknown constant, times absolute value of f of x, and then we add some function which we know how to normalize. And we add some alpha here, which is arbitrary. Then from taking rho of x like this, then we know that our transition probability in the Markov chain has to be that quantity. Okay, that's just from knowing what Markov chain is. Okay, so then the recipe is, when you sample, you measure two things. Okay, these two things. Let me call it V physical, such as volume. I could call it average F or whatever. But this is the quantity that I'm measuring, and this is the other quantity that I'm measuring. So this V physical, it's kind of physical weight, but the point is that it's just you evaluate the function when you measure, you evaluate the function, and then you divide by whatever we took for rho. Okay, basically this quantity that we took here in rho, you divide by this one. Okay, and on top is the function itself. And then we measure another quantity, which is alpha times this function, this addition of fake function. Okay, and you divide by the same quantity that enters in rho. Okay, that's my choice. These are the things that I'm going to measure. Okay, so instead of measuring, for example, average energy or measuring the average energy square for specific heat, I'm actually measuring these two things, and I'm taking the transition probability to be basically this. Yeah, this is my transition probability. Okay, and I'm running in the usual Markov chain, the same way that we did the Heisman model. So then the question is, what is really V physical? I mean, what does it converge to? And what is V alternative? What does it converge to? Well, we know from theory that V physical is actually this quantity, is integral over all possible configurations, or you could say it's a sum over all possible configurations, but it's the same as if x is continuous quantity, then it's integral of all possible configurations. This dx has lots of dimensions, of course. Of rho of x, this tells you how often do we measure, how probable is to visit certain configuration, isn't it? So this is this is like in Ising simulation, this was the Boltzmann weight, doesn't it? So this part comes from the fact that we are accepting the step with this probability, Boltzmann like or rho-like probability. So this comes from the fact that we have a Markov chain, and then this is what we actually evaluate. So this is this, isn't it? F of x, average value of divided by f of xc, alpha fm. Okay, but now the point is that rho itself is, as we said before, rho itself is constant times absolute value of f of x times alpha fm of x. Now you see the nice thing that this thing here and this denominator here, they cancel. Well, that's the reason that we choose put this in the denominator. So they cancel, and what you get is just the constant times the integral that we're really looking for. Okay, so now you see that if we were measuring only v physical and we didn't have the alternative thing, we would determine integral times a constant, but we don't know the constant. Okay, so because we don't know the constant, we know the integral up to a constant, but that's not a useful thing, isn't it? We know them, we need the number. So of course, if you integrate a lot of integrals, let's say projection to something, then you could get a lot of integrals at the same time, but they were all determined up to the constant only. So how do you get the constant? Well, in order to get the constant, we measure this alternative thing. Okay, so what is then this alternative? Well, it's easy. Rho of x is, as before, this constant times f of x alpha fm. So we have that. Then alternative, this v alternative then has this extra alpha fm, actual value of fx alpha fm. So, and these two will cancel, and we're going to end up with c times the integral of this fake function or this normalized function times alpha. And now you see that this integral here is known, and we actually required that this function is normalized. So if this function is normalized, this integral is 1, and then we're left with c times alpha. But that's nice. See, now I can take the ratio of these two quantities, ratio, okay, and the constant c, which we don't know, cancels out from ratio. See, and then we get that this ratio is then integral of desired integral that we're looking for divided by alpha. Alpha is a constant that we input. It's an input that we know. This is the quantity that we see. We just cook up some alpha here. We know what it is. So we see that then that basically we know all the quantities. We know v physical, we know v alternative, we know alpha, so we know the integral. So we can express then the integral from this. The integral is alpha v physical divided by v alternative. Now, you also see that if we set alpha to 0, let's say that we decided that we will set alpha to 0 so that we take only absolute value of f of x as our weight. So alpha goes to 0. What's going to happen? Well, then integral will be alpha, which is almost 0, but also v alternative will be almost 0. I mean, why? Because well, it has also alpha in here. So we will have 0 divided by 0, which will be very imprecisely, which will give you lots of noise and very imprecise determination of integral. I mean, as long as alpha is finite, it should still work, but it will not be as efficient as alpha if alpha is appropriate. Yeah. So of course, if alpha is very, very large, on the other hand, then things are not that bad. In this limit is actually better, because what does it mean that alpha is large? Let's say that alpha is very large. Then basically we don't take the weight to be proportional to the absolute value of the function, but it's going to be just proportional to this alternative function, whatever that alternative function is. So in this case, alpha will be very large, v alternative will be very large. So we have large number divided by large number, which is not so bad. And then times v physical, which is going to be also something. And then the weight, this ratio is not going to be that bad. I mean, it's not going to be optimal, but still reasonable. The problem with this is that, of course, if this alternative function, this f of m of x, is very, very similar to the absolute value of f of x, then we basically didn't lose anything, because these two functions are just the same functions, isn't it? So actually, it doesn't matter what you take for alpha; it can be very large as well. So we are going to actually visit such configurations in which this alternative function, this our fake function, is very, very large. So let's say that the large pole or large divergency is resolved by the function fm of x. If that's the case, well, let's say that the both functions have the same divergences. Okay, so both functions have exactly the same divergences. Then taking alpha very large is going to be okay because we are going to visit all points where absolute value of x, f of x is large. So both functions are large at the same place, so that's not a problem. The issue is that most likely, because our function is complicated, we will not be able to guess a good function such that both functions are similar. Usually that's very hard. That's if you know, then you basically solve the problem. So these two functions are not going to be that similar. Okay, so then of course we need to be more careful. It's a good idea that we spend most of the time in the places where the absolute value of the function itself is large, and only some smaller amount of time where this fake function is large. Okay, of course, the two will share some space in which both are large, of course. But I mean, there are still a lot of spaces probably where the absolute value of the function is large, while this one is not large because we didn't do the proper ansatz. We did not know. It's hard to determine this absolute value of the function. So the point is, we want this alpha to not be too large, in the sense that we still want to sample mostly the original function, absolute value of f, okay? But we are adding a little bit of this fake function in order to be able to evaluate this integral by this ratio, okay? So we don't want alpha to be too small, okay? Because then we will have 0 divided by 0. That's not good. But as long as these two are of the order of 1, then it's not a problem. So the question is then, what is the good value of alpha? So basically, of course, as always, alpha is going to be self-consistently determined. So we were going to adjust it during the simulation. We will take alpha to be some arbitrary number at the beginning. Then we will run for some time, and then we'll say, okay, we can change alpha now and adjust it so that the question is how? Well, it turns out that the good rule of thumb is that so that this V physical, the V physical is of the order of V alternative. They can be more or less the same, but it's maybe slightly better if V physical is like a little bit bigger, like, I don't know, 5 times bigger, 10 times bigger. I mean, shouldn't be million times bigger, because then million is huge. But if these two are the same order of magnitude, preferably V physical slightly bigger than V alternative, we're going to do just fine. Okay, so of course we need to adjust alpha. Then alpha is going to be more or less the same as the integral, because these two will be more or less of the order of 1. Okay, so we need to adjust alpha self-consistently in such a way that this is satisfied. Now, again, the reason that we want these two to be of the same order of magnitude, or maybe physical slightly bigger, is because we want to move in the space in which the absolute value of the function is large, rather than the space in which the fake function is large. I mean, we need to go a little bit into the space where the fake function is large, but we mostly want to be in the place where the real function we want to calculate, is large. Okay, so I hope that this is now much more clear. So what's the goal? The goal is we invent we decided that we're going to put this charge, density, probability density, to be proportional to absolute value of function, and we added to it some known function, or known function which we know the integral, with some constant alpha, which alpha is arbitrary. We measure these two quantities, okay, and we derive that these two quantities are basically, from these two quantities we can calculate then the integral, and that's what we want. Now the only question is how to determine this alpha and how to determine an FM. So this, of course, is a little bit of an art, but nevertheless, what are good choices. So as I said, alpha is kind of easy, so that these two spaces are visited roughly in the same order of magnitude, maybe physically a bit more. But what is the good choice of Fm? Well, we already said Fm should be close to the, would be nice if that Fm is close to the absolute value of the function. But of course, that's very hard to achieve. The most important thing is that it should be normalizable in the sense that we can calculate integral of this function exactly and make it 1. Okay, if you can calculate exactly, then it's a good idea to make it normalized so that equations are simpler. Okay, so as we discussed last time, there are of course obvious choices. So one choice is to do the same as in Vega's algorithm. So we just choose that this function is a product function, where this x has lots of components, x1, x2, xn, and then for each component we choose some unknown function, but then this unknown function is basically just a projection of the absolute value of the function to all the x's. Okay, so when we measure, when we do the random walk, in addition to calculating these two v physical and v alternative, we're measuring this when we do the random walk, v physical and v alternative. These two things we are measuring, but then in addition to these things, we can also measure all these projections. Okay, all the projection to all the x's, and then for those projections, we can then construct this measuring function. Okay, so this is basically the same as Vegas, and also the performance is similar to Vegas. So now there is a little issue here that I want to point out. So typically we cannot afford too precise mesh. I mean, we're always limited with a few hundred points. Okay, and therefore we want to make absolutely sure that we don't have systematic error. So even if you have 500 points and you calculate integral with 500 points, if the function is kind of complicated and basically have lots of noise when you sample, your function will look non-continuous. And then if you use some high order numerical integration of this non-continuous function, you will have lots of error. So therefore, it's a good idea to avoid systematic error to use functions which you can exactly represent on a computer. So one of those functions you can exactly represent is just stepwise function. Of course, we could also use function which is exactly linear or exactly quadratic, but stepwise is kind of obvious choice. So we choose this gi to be a stepwise function. So it's a number within some small delta h, and then it's another number, and two delta from delta h to 2 delta h, another number, so on. So we have this equidistant mesh, hopefully. I mean, usually equidistant mesh is just fine. And then we take just some constants in each interval. Okay. Why? Because in this way, we know the function on a computer exactly, not approximately. Because usually, of course, in a computer, we think of a continuous function, isn't it? That we know on discrete values. Of course, if the function itself is continuous, that might be a very good approximation. But when we do Monte Carlo, we typically have lots of noise, and then function might look like that. And then approximating this with a continuous function might not be a good idea. So let's say that we are working with discrete functions, which have this property that gi of x is some constant if x is within this bin. Okay, so then the integral of such a function is really simple. It's basically just delta h, which is the length of this integral, times sum over all values. Okay, so in this case, the integral is actually even simpler, and implementation, at least in this case, is really not a big deal. And the representation of the function is exact. And so basically for this case, you can easily now just compute the integral. So this integral is just the product of all the integrals on projections of all dimensions, but these integrals are really just delta h, which is the size of the mesh bin, or the bin in the mesh, times the sum of all numbers that you have in this in these bins. And so now you see that you can take any number of bins, and it doesn't need to be large. You can just take only 10 bins if you want, or you can take 50 bins, you can take 1,000 bins, whatever. This representation is exact, so you don't need to take the limit of n very large. Okay, so now, of course, as I said last time, with this method, we have now complete method. We can start calculating integrals. However, this method is now not much better than Metropolis. Vegas, because Vegas does the same thing. So it resolves things which are when the peaks are on any axis, but of course it doesn't do anything spectacularly good when the divergences are somewhere else. However, in physics, we have very, very commonly the peaks which are kind of on the diagonals, which look like convolutions, and therefore, in this case, when we do Markov chain, we can cook up functions which have an ansatz that is much more complicated and much more general. Okay, and therefore this method has an advantage. Again, the example is that we can cook up a function that is the product function. So this part is just product like before, and then in addition it has some extra functions hij, which are like correlations between two dimensions. So correlation between dimension y and dimension I, which basically means that we are looking at a diagonal between the two dimensions. And then, of course, these quantities on the diagonal are, of course, the projections of our original function, absolute value of f, to that diagonal. Or basically, it's the correlation between the two dimensions, isn't it? So in physics, many times, what's important is not only the projection to all the directions, but also the correlations between different directions. So typically, we have, I don't know, like three-dimensional vectors, and then the correlations between the distances between two particles. That's what's important, isn't it? Because you have two forces between two particles, for example, and these correlations are the most important ones. So the important point is that we can. So if the function has this ansatz, which looks a bit more complicated, we can still work out the integral of this function fn of x dx in terms of the stepwise gi of x and stepwise hi y. So these formulas that you need to work out for such a function are slightly more messy, but are doable. I mean, you can work out everything. And I, at least in this notebook that I shared with you, it's on the homepage, this is worked out. But I don't want to derive this here, and kind of it's hard to follow in class. But believe me, it's doable. So the important question now is whether this derivation here is more clear to you than last time. In other words, do you understand? Can you answer either in the chat or unmute your microphone and tell me, was this understandable?
Yes.
It is.
Yeah, the idea is not hard to understand, but I'm wondering if coding is difficult or not.
I mean, it's not that difficult. I mean, okay. So if you want to know how difficult it is, I prepared this Python node, Jupyter notebook, hide_int, okay, where the implementation is done. I'm not going to go through it, but I can show you how it looks like. So it's this integrated by Metropolis 2, okay, and this is the 3D integral. So basically, it's a large. I think it's done for n 3D integrals. So therefore, it's a little bit harder than 1D integration. But altogether is not so hard. So here we go over this loop of over all iterations, very large loop. This is like in simulation of the Ising model. We decide which I call it loop, but basically which variable do you want to change? So we change one of the variables. And then basically you can change so-called external variable, because we want to calculate here lots of integrals, not just one. This is the problem. This is similar than the problem I gave you for the homework, the last part of the on this Vegas algorithm. So we are sampling lots of integrals. So therefore, this case is when you change this external variable, and this case is when you change any other variable. And the reason that somehow the steps are slightly complicated here is because we're in 3 dimensions and we're using spherical coordinates. So don't get scared. This is just because spherical coordinates in 3D space are slightly more complicated. I told you last time that, some time ago, that there is an additional trial step probability, which is non-unity in case of spherical coordinates. So therefore, this step is a little bit more messy. But I mean, if we were doing, if we're not in 3D or not in spherical coordinates, this would be much simpler. This would be more or less this large. Okay. Now, so this is about just the step. So we are attempting a step. It's equivalent to doing in Ising model spin flip. So you just select the spin at randomly, but here the space is continuous. So you try a step, you calculate. So you have a step, and then okay, let's say the step is doable. So then you want to evaluate the function. So here we evaluate the function on this particular configuration. Momentum is actually configuration. So, but in addition to calculate the function itself, we also calculate the fake function. This m weight here is the fake function. And we multiply with this alpha. I call it V norm, but actually it's this alpha. So this value of the function has 2 components, and the 2 components are, as I said in this derivation, the 2 components are these 2. It's f of x, and this is the second component, alpha fn. Okay, so so the function itself has 2 components every time we do something. And then our probability to accept or reject the step is exactly what I wrote before. So it's the first component plus the second component of the new configuration divided the first component and the second component of the old configuration. Okay, so times the trial ratio. This trial ratio has to do with the fact that we have a trial step probability which is not symmetric sometimes. But we could also create a steps for which this is symmetric. So then this would not be an issue. And then we accept just like what we did with the Ising model. So we accept if this number is bigger than 1 or less than 1 compared to this is random variable. And then if we accept, we just update our x, or basically our momentum. We update our value of the function, and then this is just something that has to do with measurement. We kind of remember how many times we change one or the other. So I would say that this part here, which has to do with the trial with the step, trying the step or accepting the step, it's basically the same as an Ising model. So not harder at all. The only new part is this adjusting those functions which I was telling you about here. So basically, how to choose this alpha. We want to adjust the alpha such that this thing is satisfied, and we want to calculate this good projections to the function fn. So these 2 things are new, and these are basically implemented in this part. So it's not that complicated, just a few lines of code. So basically, we take the ratio of the 2 values of the function. We have 2 components of the function, and we basically this p-val sum and p-norm sum is, you see, p-val sum is, I think, yeah, p-val sum is just the sum of the second component, and no, p-norm is the second component, and p-val is the first component. So the sum of the first component, the second component over a long time. And then we take the ratio of the two components, which is exactly saying that we are basically looking at the ratio of V physical divided by V alternative. Okay, so we constantly monitor this ratio, and then we said that this ratio should be the order of 4.1, let's say, and then if this ratio times 0.1 should be of the order of 1, and you say, well, if it's very different, much smaller than 1, let's say less than 1.1, then you basically in this case we need to kind of decrease V0. Yeah, so we decrease V0 for a factor of 2. So we reduce this constant alpha a factor of 2, and then we reduce these quantities that we already accumulated, the proportional to alpha, with for the same amount. If this number is much bigger than 1, let's say 4, so we don't want to change it if the number is just 1.1 or 1.5 or 2. But if it's much larger than 1, then you want to change it. And then you decrease by a factor of 2. So no, actually increase. In this case, you need to increase. So basically, this is just checking. So every few iterations, you check whether this V physical whether V alternative is either too big or too small, and then you either multiply by 2 this constant, or you divide by 2 this constant, so that at the end of the day, this value is not too crazy. Then you print something from time to time, whether you changed something or you don't. And then, yeah, this part is basically where you project your function to each dimension, each axis, and you also project to all the diagonals. So and then from time to time you recompute. So recompute, where is recompute? See, recompute. From time to time this one. From time to time you recompute the weight, which means that this function recomputes. Actually, what does it do? It takes the current functions, the currently accumulated value. It takes the new accumulated approximations for this G of I. So we are basically sampling this thing for some time, and then from time to time we just update these functions fm of x, which means recompute. Basically, you do this for a long time, you have better approximation for G's, and then you stick them into this fake function, with which gives you function in alternative space. And so that's it basically, and then the rest is just printing out some information. So it's not too hard. That's the message. I mean, of course, it's a bit more complicated. The implementation is roughly as hard as Vegas. I wouldn't say it's much harder, but the integration tend to be more efficient than Vegas. And again, the reason for this is because in Vegas, if the function has peaks which are far away, which are not on one of the axes, the Vegas is extremely inefficient. Now here we are always gonna visit configurations where the absolute value of the function is large. Why? Because we always take the weight to be proportional to the absolute value of the function, and we add some extra function which serves as this normalization function. But we always, if this absolute value of the function is large, of course we will always visit that configuration, and therefore means that we're always going to use important sampling on the real function itself. Okay, so in this sense, this Markov chain integration is more efficient typically than, especially for very large dimensions, than Vegas. Yeah, so now I did not intend to actually go through this example. I mean, here if you have such a problem and you really want to use this, then you should read this notes. I here worked out the 1D convolution and the 3D convolution, basically how to construct the functions and how to actually evaluate these functions, these integrals. You will recognize that in this integrals, we need to do integrations of a function kn, which kind of suspiciously is related to your to one of your homeworks. So turns out that we need to do an integral such as that, and this should remind you of one of your homeworks. Okay, so yeah, so it has to do with the recursion homework. But the point is that there is some little math which you need to do in order to get these convolutions, to have the integral analytically given. Yeah, so I will not spend more time on this high-dimensional integration in Metropolis. So my goal here was to just give you some hint of how this is done. And if you have such a problem, you can now go and read and educate yourself. But we will not implement this here. So if you have any question on this subject, please ask it now. Is it clear? Is there any issue that or detail that you would like to learn? Anybody? I guess you understood now the basic concept, huh?
Yeah, it is clear.
It is clear. The basic concept is clear. Okay. Of course, there are always little details which we cannot talk about all the details here, but the basic concept is clear, and therefore you can go and implement if need be. So the chapter that I wanted to talk about is, however, slightly different. We want to minimize the function with the same Markov chain. Now, why do I talk about minimization or the integration? Well, because at least in practice, this minimization is kind of much more commonly used. So this simulated annealing is way more has way more widespread use than integration, and it's kind of also slightly simpler to implement. These are the two reasons. So I already explained last time that the idea of simulated annealing is actually very simple. In this, we again have very high dimensional function. So of course, this is not useful when you have 2, 3-dimensional function. In this case, you could just plot the function, guess where look at it and guess where the minimum roughly is, and then use the simple derivative to get closer to it, and use the standard downhill gradient methods. But if the dimensions are large, if the dimension of the function is large, you cannot plot such a function, and then something like simulated annealing is just the way to go. So in this case, we take probability to be metropolis, to be Boltzmann-like, okay, where this function f of x serves as an energy, okay. I mean, f of x becomes like an energy of the system, and then you have to introduce something which is called temperature. And of course, in general, when the function is arbitrary, it's not clear what you should take for temperature, okay. Therefore, what we're going to do is we're going to take temperature to be some very large number at the beginning, and then we're going to slowly decrease, and eventually when temperature becomes small enough, we see that when temperature is very, very small here, then this exponent becomes, of course, a tremendous function. Has a tremendous value when function f of x is bigger than the minimum value. So when the function f of x has a minimum, then this number is the biggest number. And when f of x is bigger than the minimum, then of course this probability decreases very quickly, exponentially quickly. So therefore, this probability, when temperature is small, this probability is large only near function where near the places where this function has a minimum. Okay, so therefore, physically we know that when temperature is 0, we should reach the configuration where the energy has minimum, or basically energy is now this function f. So we are going to end up in the minimum of the function. Okay, so I guess the idea here is even simpler than the high D integration, isn't it? The idea here is completely trivial. So you have a high dimensional function and you treat it more or less like your energy. You just decide, okay, this quantity f is like an energy for some physical problem, and then I will introduce some temperature, and then I will change the temperature slowly. And physically, we know that when temperature is 0, I'm supposed to get into the ground state. Ground state means the place where the energy is the smallest. So simple. So let me read this through. I guess it's kind of obvious. It's technique. This technique uses metropolis to find global minimum function of many variables. It's typically used for large-scale problems, especially ones where desired global minimum is hidden among many poorer local minima. Now, what I wanted to emphasize here is that, let's say you have a function which has a very, very large number of minima which are equally deep, let's say. Okay, so you have such a case. We have very, very many which are almost equally deep. This is basically almost unsolvable problem. I mean, even simulated annealing will not do it. Simulated annealing will eventually end up in one of the minima. Okay, it can't help you. At high temperature, of course, we're gonna jump all over the place. We're gonna go back and forth and back and forth. But once the temperature is 0, we will end up in one of those. So you can't solve that problem really. This looks like a quantum mechanical problem for tunneling, doesn't it? But as long as one of the minima is slightly deeper than the rest, then if you run the simulated annealing slowly enough, then we know from physics that we are supposed to go to the ground state. Okay, which means that if one of the minima is lower, we are supposed to get to the ground state, provided that this annealing is slow enough. So temperature is changing very, very slowly. Now, of course, in practice, we cannot change it infinitely slowly. So we might still end up in local minima and the global, but still the hope is that for reasonable slow changing of temperature, we are probably or likely end up in global minima. So this class is finding a local minima, global minima of a large dimensional function is NP-complete problem, whose computation time increases exponentially with n. So, and this was basically unsolvable until 1983, when this gentleman invented this simulated annealing. So this, of course, simulated annealing, as I said, does not solve the problem exactly, because it does not guarantee that you're going to get the global minimum. But in most cases, we just need a reasonably good solution, even if it's not the one with exactly the lowest total energy. So one of the problems that you might be able to solve now is to help Rutgers to schedule classes in such a way that classes never collide for a student. You know, recently we decided, or basically our bosses at Rutgers decided, that we need to change the times in which different classes are running. And since Rutgers is a very large institution, this was a tremendous problem. We had to hire some external company that does that. But actually what they do is they run simulated annealing, exactly this thing, this algorithm. So we professors need to put in certain constraints of when we are available, when we can't teach. Then students need to put in which classes are gonna which classes want to or they enroll. So you all give your information about which classes are you enrolled to, and then the constraint is that 2 classes should not run simultaneously, isn't it? And then you have a large minimization problem. So you need to find the times for all the classes at Rutgers in such a way that no student will have two classes at the same time. Okay, and at the same time, constraint is that the classes need to run, let's say, from early morning to late evening, and professors have particular time during the day when they are available. Okay, so and with such simulated annealing, you could solve this problem. You don't need a company; you can do it yourself with a little bit of Python coding. Okay, so yeah, we are going to do a slightly simpler problem. Okay, rather than figuring out all the constraints for every student and constraints for every professor, and then optimizing the schedule for all the classes at the university, we're going to do so-called traveling salesman problem. So the problem in traveling salesman problem is the following. We have n cities which are indexed by 0 to n minus 1 with given position Ri. So these are arbitrary positions in space. And the traveling salesman problem needs to visit all the cities in such a way that every city is visited only once and only once. Okay, so that's a similar constraint as let's say that every student need to visit the classes which he or she registered for. Okay, a similar constraint, and of course in classes we know that the classes for every student should not overlap. So here it's different. It's basically positions of the cities are given, they're fixed, and then this seller needs to visit all of them and return eventually finally to the city of origin. But each city needs to be visited only once, and the route needs to be made as short as possible. Okay, so here the ultimate goal is to use as little gasoline as possible, because you want to find the shortest possible path. So this problem, of course, belongs to NP complete problems. Computation time increases exponentially with n, and simulated annealing is like a perfect method for that. So this is the problem that we're going to solve. But before we go there, I want to discuss the algorithm. So what is the core algorithm for solving that problem? Well, here's the description, one page. So we slowly decrease the temperature in order that the system relaxes into its ground state. But in practice, how do we do? Well, we pick an initial configuration X, which of course is very, very far from ground state, anything, and some initial temperature T0. So the important point is that T0 should be much higher than the changes in function F to be minimized when typical Monte Carlo step is taken. So if you have no clue about the function F, then just take some very, very large temperature at the beginning, and that's it. Okay. So then what do you do? Well, you have then a long loop through decreasing temperature. So change the temperature slowly. So what do? You pick a temperature, you equilibrate at this temperature using metropolis with selected allowed elementary changes in the system. Yeah, so this is of course an issue here, allowed elementary changes in the system. So in other words, you have to invent some steps with which you're gonna make moves, okay, moves. And that's actually the hardest part of the problem. So once you know good moves for your problem, then you know that you're gonna quickly find or efficiently find a global minimum. For Ising model, we were discussing two possible moves. One is flip a single spin. The other one was flip a domain. Okay, but in traveling salesman problem, there is no such simple thing as flipping a spin, isn't it? So you need to invent better moves. Okay, and we'll discuss what the good moves are. So then the system is equilibrated when the rate of the change of function f averaged over some number of Monte Carlo steps is small. So the idea is that we run metropolis at particular temperature quite some time, so that we're sure that the system has equilibrated at this temperature. What does it mean equilibrate? Well, imagine you have a function like that, and the temperature is, for example, here. Okay, so equilibrating means that if temperature is here, we need to kind of jump all over the place where this function is of this order of magnitude. So when you reduce the temperature, let's say the temperature is like this, then equilibrating means that we are going to spend a lot of time in here because this has the deepest well, but sometimes we're still going to jump here because we could also be here, and maybe we're going to even jump here because this also has something. But nevertheless, we're going to spend here, because it's deeper well, much more time than in the other two. Okay, so when the temperature is such that you can still jump across. Okay, so of course, when the temperature becomes sufficiently low, then we are the probability to tunnel through it's going to become very small. It can still tunnel sometimes, but the probability becomes small. So hopefully by then, when the temperature is here, we are not going to tunnel through anymore. We're going to get into global minima. So that's the idea. Now, we have to measure the thermal average of this function f. If f does not decrease at this temperature compared to the previous temperature, we are done. Okay, so let's say that when the temperature is here, we still might be jumping a little bit from here to here, and the function is still going to change. But once the temperature is low enough that we are basically stuck in one of the minima, and the function doesn't change anymore, the average of the function doesn't change anymore, then we are done. We don't need to continue anymore. So once the function once f does not decrease anymore, we are done. We can exit the loop. But if the function still decreases, then we need to decrease the temperature. For example, divide by decrease the temp by 10%, and then rerun until function still is minimized. Now, of course, this reducing the temperature by 10% might sometimes be too fast. So 10% is not slow, maybe. I mean, for trivial salesman problem, it works pretty well, 10%. But if you have more complicated problem, you might need to reduce temperature for 1% and run a long time. Okay, so how much to reduce temperature? How big needs to be temperature at the beginning? And what are the elementary changes? These are the complicated questions. This is something that depends on the problem, and you need to invent for each problem different set of numbers. So this part explains that actually what the temperature is non-trivial problem. So sometimes it's not clear at all how big the temperature needs to be, but it has to do something with the function. So the typical value of the function. And of course, the moves are the difficult part. I mean, what to take for the moves is highly non-trivial. Okay, so trivial extension problem. So I discussed here. Trivial extension problem is like this. So if you have 100 cities, so then there is one city here, 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 here, and you can see that the path that computer chose after lots of minimization looks like pretty good path, isn't it? So this path looks pretty good. So there is no crossing. You see, whenever you see a crossing like this, so like that, isn't it? Then you know that the path is not optimal. Okay. So here is the 100 cities. Here is the 1,000 cities, isn't it? You have 1,000 cities, and you see the trivial extension problem never kind of crosses, because crossing means that you definitely can reduce the path further. Okay, so the computer code did pretty well. Now, if you have cities given like this, so let's say that the cities are in all these points, what is highly non-trivial, in my opinion, is to figure out what are the elementary moves. So what would you choose? What would you choose for a move? This is not an Ising model where you just flip a spin. Okay, so what you could do, of course, is you could reorder the way the cities are visited. So your input is the position of all the cities, doesn't it? This is your input. So where these dots are. And then your configuration is basically just a permutation in which order the cities are visited. So it's a permutation of integer numbers. All numbers between, let's say, 1 and 1,000, you could configuration is a permutation of numbers between 1 and 1,000, and any permutation defines one possible path, isn't it? So we need to now figure out which path is the 0. There is a crossing between 0.03 and 0.5. Let me see. Yeah, you are right. There's a crossing here. So well, maybe this was not running. This was not running long enough, or yeah. Well, maybe it's a critical case. So the question is whether this path like this, isn't it, like this, would be shorter than the one with the crossing. It's not entirely clear to me that it would be shorter, but somehow my eyes says that it would be shorter like that. So the crossing, this crossing does not look the best indeed. Yeah, this solution is a reasonably good solution. Of course, if you want to have an even better solution, you need to reduce the temperature even slower, maybe. Yeah, I mean, this doesn't guarantee that the path is exactly the shortest. And yeah, probably if there's a crossing, most likely there's a slightly shorter path available. Thank you. Yeah, but what I wanted to explain is what are the basic moves. So here is the explanation. As a problem in simulated annealing, as a problem in simulated annealing, the traveling salesman problem is handled as follows. So what do? We take configuration. Configuration, the cities are numbered from 0 to n-1, let's say, and each has some coordinate. Configuration is a permutation of the numbers between 0 and n-1, interpreted as the order in which the cities are visited. So as I said before, if you have a configuration like 0, 1, 2 to n-1, this is one possible configuration, isn't it? You can have another configuration which is, let's say, 2, 1, 0, and so on, n-1. And basically the two configurations are the configurations in which you visit the cities in a different way. Okay, so both are actually just permutations of these numbers, isn't that, between 0, 1 to n-1. So permutation is clearly a configuration in this case. So how do you change permutations? That's the question. What is the elementary move? What would you choose as elementary move? And here's the explanation. There are two moves that are commonly used and seems to be pretty efficient. And I explained here. I will try to be careful. I will try to explain you what exactly this is. So a section of path is removed and then replaced with the same cities running in the opposite order. Okay, so let me read again. A section of path is removed and then replaced with the same cities running in the opposite order. So I guess not clear at all. But let me demonstrate this with the figure. So we have, let's say this is one of the current paths that we have. So this is the path we currently have, my sketch. So then I randomly choose two cities, let's say n0 and n1, randomly, any two cities, but I choose randomly two numbers, two integer numbers, which corresponds to two cities. And then I look at the path between these two cities. Okay, there always should be a path between two cities. Any two cities, there should be a path. And then what I do is, as I said, so a section of path is removed. So we remove this section and then we replace with the same cities running the opposite order. So what does it mean? Well, we keep the same path here and we keep the same path outside. And then we we add a crossing. So in case there was a crossing before, we remove it. In case there was not crossing, we add it. Okay, and then of course we're doing metropolis, which means that if this path is shorter, we keep the shorter. If this path is shorter, we keep this one. If the path is longer, we might still accept it if the temperature is finite. If the temperature is 0, of course, we're never going to accept the step which has longer path. But if the temperature is finite, we're still going to jump between these two configurations, even though one of them is more expensive than the other. Okay, so this clearly is a move to avoid crossing, isn't it? Or to remove crossing. So in this case, where the crossing is found, actually something that you know, we could, if we run this thing sufficiently long, I think that this crossing could be eliminated to exactly this move. Probably wasn't run for a long enough time. So this is one move, but in addition to this move, there is another move that seems to be pretty useful. So the other move is the following: a section of path is removed and then replaced in between two cities on another randomly chosen part of the path. Clear, huh? Completely clear. Not to me, but let me repeat once more. A section of path is removed and then replaced in between two cities on another randomly chosen part of the path. Here's the sketch. So we randomly choose not two cities, but three cities now. So we have city 0, city 1, and there is a path between the two. And then in addition to this two cities, we select another city which is outside that path, which we call N4. Okay, and then once we have all these three things, we are going to reconnect them. In which way? In such a way that once the path from N0 to N1 is done, we're going to jump directly to the city after N4, and then we're going to go through the old path. Then no, we shouldn't go to N0. We should go to N1, and then we go like this, and eventually we get to N4, and then we need to reconnect back to N0. Okay, so the point is we randomly select N0, N1, and N4, and then we reconnect them in this complicated way. So the path between N0 and N1 is untouched. The path between N4 and N3 is untouched. So this is N3 is the city before N1, N2 is the city before N0, or N3 is after N1, and N2 is before N0. So there is a lot of path which is untouched. So this part is untouched, this part is untouched, but these N0, N1, N4, N5, N2, and 3, these are reconnected. Okay, so these are all the moves that we're going to implement. Now, are the moves clear? Do you understand them?
I think so.
Okay, so okay, so once you understand the moves, so these are the two moves, then objective function, in the simplest form of the problem, energy is just taken as the total length of the journey. So this is kind of obvious. So our what's it called, the objective function to minimize it is the total length of the journey. So the above-mentioned moves are hardest to implement. The following plot explains them in the example. So yeah, so basically these are the moves explained here in the example. And here we have an example of calculations. Now, I prepared implementation of this in one Landau, no, Trailing Salesman problem. So this Trailing Salesman problem is available in either GitHub or online in our webpage. And I'm gonna try to go through this implementation quickly, and whatever we don't finish today, we can finish next time, since we have one more, which is good. So I'm gonna restart the kernel and clear output. First, I'm going to just evaluate everything so that I show you how it works, okay? And then I'm going to start explaining the details of the algorithm. So let me just run it. So distance and total distance, and then at the beginning, I'm just going to plot the initial configuration. So this initial configuration is basically just we select cities at random. So here we select cities with a completely with random number generator. So they are completely randomly distributed in the 2D space. We could take I don't know something from the map, from geography if you wanted to, but I mean for our purposes, randomly generated cities are just good enough to see whether the algorithm works. So and then the original configuration from which we start is just the permutation which is ordered. So basically 0, 1, 2, 3, 4, 5 to n minus 1. And this original permutation looks like that. So the total distance is 50.296 for I think 100 cities. As far as that, yeah, I'm doing 100 cities. So that's how it looks like. So I mean, obviously this journey is way too long that need be, isn't it? Because we see crossing all over the place. So then we are going to implement this move. So this is one of the moves: find the segment, then reverse, then find another segment, transpose. So these are the moves. I'm going to discuss them next time. Then we evaluate this for one particular example, what the move does. And then here is the actual algorithm. So here's the algorithm where the trial excision problem is run for a long time and the problem is minimized. Again, I'm going to only evaluate it today. Yeah, so this is the algorithm, and now we're running it. Here we're running it, and you see we started with something like 50. Was the journey. So after a first few at the first temperature, we already got to 31. Then we reduced the temperature a little bit. We got to 24. We reduced a little bit, still 24. We reduced 26. We reduced 23, then 21. And you see every configuration seems like a little bit less crossings, isn't it? That crossing, less, and well, so the temperature now is 0.05, the distance 11.4, the distance 11.4, 11.2, 10.9, 10.04. You see most of crossings are now out. There's still some left. 9.4, 9.2, 9.1, 9.0, 8.8. So, and okay, so now, well, there's still one crossing here and one here. So there's still some, one here. So there's still some left. But here, I don't see any crossing yet. But that doesn't mean that, of course, the minimum is the smallest, not necessarily. So we are still at distance of 8.4, 8.4. We're still moving some changes, 8.3, and so on and so forth. And eventually, after many, many more iterations, we managed to get to 8.1. So 8.13, and I think here it stops because the changes, you see, here we still have accepted step, 4 accepted steps. Here we have 4 accepted steps and so on. But eventually, the number of accepted steps becomes 0. So it means that the last temperature, which is 0.001, the distance did not change at all. We didn't have any accepted step anymore. And the way that we connected them here seems to be pretty close to the minimum. Of course, not guaranteed to be the minimum. We would need to run way slower and longer if we want to have better solution. But this is, for practical purposes, such solution is pretty good already. Okay. And as you see, it didn't take that much time. It wasn't that hard. Now, what are the moves? I will explain this next time. So basically, finding segment for the moves and how to how to calculate what is the cost of this move, and then how to actually evaluate the move. This is code. And then this is for the other move. We have two moves. One is called reverse, and the other one is called transpose. We have two moves. And once you have these moves implemented, then the traveling salesman problem is really simple, only a few lines. Okay, so is there any question?
I have questions.
Yes, please.
Okay, so with the moves that we had, the two moves that you showed, the cycle, the length of the cycle is computed after every single permutation, right?
The length of the cycle. Let me understand what I mean with that.
Of the whole path. Like you make you have a path, you're given some random path, you make one permutation, and then in order to verify it, you have to compute the whole thing of each step.
No. Very important. So you see, when you make this move, it's very easy to recompute the traveling distance, isn't it? So the traveling distance, you remove this part of the path and this part of the path, and you added this path and this path, isn't it? So you can really just update the length. So you remove this and you remove that, and you add this and you add that.
Okay, so you can maintain everything you haven't changed. That makes sense.
So the important point is that indeed the updates need to be simple enough. So if you had to recompute the entire distance every time, that would be slow. It's not a good idea. It's much easier to just update the path. Now, of course, here the path is slightly harder, but still, I mean, most of the path is the same. So this path here is the same, and that path here is the same, and that path here is the same. So most of it is still the same, but there are, of course, these are the new paths, and before these are the old paths, isn't it? So you have to remove something and you add something, but it can still be just updated. Very important, yeah. Okay, any other question?
We're going to be talking about this next class too. We're finished with this.
Yes, I wanted to present this next class indeed. So the implementation, although I don't plan to give you homework on that. So I don't know if that's a good idea, because then some of you might not be that interested in the problem, but I still hope that you're interested and you come and listen to it.
I can hold off my questions until then if we're going to go into more detail in the last class.
Yes, I plan to go into details, yes.
Okay, thank you.
Thank you. Okay, so you can, I'll start.